Most ideas that wash up in Sweden and win a Nobel Prize are scientific progressions, ideas that build on ideas. But occasionally, a single powerful innovation, unconnected to the work of other prize winners, takes the honours. These are 3 such stories. The first concerns the lighthouse. For those who ply the seas, the lighthouse is a navigational reference, a warning of peril. But in centuries past, these beacons are hard to maintain. They're often in remote and dangerous spots. Early beacons burn wood. By the 19th century, they use oil and they have flashing mechanisms. But automation is desperately needed. Lighthouses that run without the constant attention of keepers. In the first decade of the 20th century, this Swede, Niels Gustav Dahlin, develops such a lighthouse. He introduces acetylene, an alternative to oil, conventional gas, even electricity. He invents a burner and a valve mixing 1 part acetylene to 10 parts air. The light is brilliant and cheap, an automated system safely utilizing a highly explosive gas. A lighthouse beam projects from these lenses. While he's not their inventor, the power that rotates them is Dahlin's idea. They're driven by heat generated in the burner as acetylene combusts. The beam itself is collected and focused by concentric rings of prism-shaped lenses. And here's another Dahlin automation, the mechanical mantle changer. Human hands are no longer needed. With its pencil beams of light, the Dahlin automated lighthouse is a triumph. It doesn't dispense with keepers, but cuts chores to a minimum and allows periods of unmanned operation. And this, a century ago. But what about daylight? It's a shameful waste of acetylene if there's no one in Dahlin's lighthouse to switch off the light at dawn and on again at dusk. His answer is to invent the sun valve, an ingenious heat-sensitive switch that means his lighthouse shines only at night. But Dahlin's genius extends beyond land beacons to lightships and buoys. As they bob in the water, he helps stabilize them with a so-called lens pendulum. Tragically, an explosion robs Dahlin of his eyesight as he tests safety devices on cylinders of acetylene. Later that same year, he wins the Nobel Prize in Physics. It's a controversial award, for some critics believe it's a sympathy vote. Nevertheless, Dahlin's legacy survives to this day in automated beacons the world over. As every livestock farmer knows, spring, summer and autumn are the easy times in temperate climates. Provided there's rainfall and it's not too hot, grass grows aplenty. But in winter, when grass doesn't grow, cattle must have good edible fodder to put on beef and sustain milk production. For revolutionizing the conservation of fodder, this Finnish biochemist, Arturi Ilmari Virtanen, wins the Nobel Prize in Chemistry. Virtanen works in the dairy industry. Much of Finland's milk goes into butter for export. His job is to improve its quality and marketability. To that end, he heads a laboratory. Virtanen discovers that if sodium phosphate is added to the salt in butter, it stays good for months. This means butter can be stockpiled, held for export till prices are best. With green crops, harvested and stored for winter, Virtanen sees parallels. The younger the grass is cut, the higher its protein value. Hay, which is cut and dried in early maturity, has less protein than young grass that goes for silage. Virtanen experiments on how to make fresh young forage into silage that doesn't rot. He knows that when silage ferments, it produces lactic acid. As acidity builds, this stops fermentation and pickles the silage. By adding a cocktail of acids to new silage, Virtanen shortens the time to where fermentation stops. As in butter storage, the acid-alkali balance is crucial. Virtanen's cocktail is a dilute mixture of hydrochloric and sulfuric acids. They do the trick. Silage making the Virtanen way. The key is an airtight silo packed with short chopped forage. On goes the acid, and the dancing starts. The purpose is to compact the silage, to squeeze out air and release the juices that start fermentation. A little more acid mix, with formic acid eventually replacing sulfuric. And finally, earth, heaped on a layer of paper to seal the silo tight. It cooks for 3 or 4 days. Then the wooden sides are removed. The exposed forage is only part of the silo, the rest is below ground. The exposed portion is now sealed with earth and clay, vital in keeping the partly fermented silage succulent, slightly sour and palatable. Thanks to Virtanen's pioneering, more permanent silos are soon constructed. The shape doesn't matter, airtightness does. In some early silos, architectural niceties incorporate a window. Silage sweeps the world. It's the premier winter fodder. Made well, silage keeps sweet for months. And cattle love it. Mosquitoes, bloodsuckers and purveyors of disease. They spread malaria, just as body lice carry typhus, and fleas the plague. Locusts destroy crops. Insects, especially in warmer climates, are pests. Their effects often lethal. In 1939, Paul Hermann Müller has a solution. He discovers that this molecule is toxic to a vast range of insects. It's called dichlorodiphenyl trichloroethane, better known as DDT. It seems the perfect insecticide. Müller, a Swiss industrial chemist, discovers DDT kills by disorganizing the nervous systems of insects. It catches on fast, used by dissolving DDT powder in kerosene. The advantage is that DDT doesn't appear to harm plants or warm-blooded animals. Nor apparently does it affect us. It simply devastates the pests that do. The colonial authorities in East Africa embrace DDT with enthusiasm. They launch a campaign to encourage people to spray their homes. It's explained that mosquitoes carry malaria and DDT knocks them out. Some elders are unconvinced. To allay their fears, a bowl of porridge is sprayed with DDT, and the district entomologist consumes it with missionary relish. The world goes mad for DDT. It's such a stable chemical that its toxic effects last and last. DDT offers a disease-free, pest-free future. A dream come true. For discovering the insecticidal properties of DDT, Paul Müller wins the Nobel Prize in Medicine. But this dream is soon over. Problems appear in the 1950s. Mosquitoes and many other insects rapidly develop resistance to DDT. And as it loses its bite, malaria returns. The objective of global eradication is lost. Today, malaria remains one of the most prevalent serious diseases. There are more problems. DDT kills helpful insect predators. It persists in soil and water. Residues build in the food chain, ultimately poisoning birds and mammals. DDT and this sort of spraying are now banned in most of the world.